Hello, everyone. My name is Yusuf, and I'm the team leader for this project. Our team consists of two more biomedical engineers, who are Hussein and Dina, a computer engineer who is Jasmer, and an electrical engineer who is Ryan. And I'm the industrial engineer for this project. Our project is about creating a component sound analysis system for extracting and analyzing medical information from patient encounters. Here's the poster of our project. As you can see, here's a picture of our system assembly in the middle of the poster, and we're going to be explaining our whole project throughout this video. Here's the problem we're facing. When a doctor is diagnosing a patient, more than 30% of the information about the patient comes from nonverbal cues. By nonverbal cues, we mean breathing sounds. In a routine doctor-patient interaction, much of those breathing sounds are never recorded and are always lost. Our suggested CSA system will be used to record those breathing sounds and mathematically analyze them. And the breathing sounds are pretty crucial to diagnose patients who have a respiratory illness, chronic or acute. Our analysis will include 10 acoustic features. Those features are harmonic to noise ratio, noise to harmonic ratio, energy entropy, short time energy, zero crossing rate, spectral roll-off, spectral centroid, spectral flux, jitter and shimmer. And our design has 4 special features. It's cost efficient, it's simple to operate, it needs a small space, and it has an easily modifiable code. Our system will also be able to display the graphics of those analysis on a monitor display screen, and it will be able to save the recorded and the calculated data after each interaction.
All right, so taking a look at the system block diagram, we can see that for the component sound analysis system, we have an entire system powered on USB. This ensures that the user is easily able to plug in one cable for power for the entire system. Starting with our input, we have the Shure SM7B as our current microphone, which is plugged in via XLR to 1/4-inch cable that's plugged in directly to the PiSound receiver. This PiSound receiver is directly mounted on top of the main Pi 4 board, which interfaces with the rest of the Pis inside the system via a network port dock. This entire system is cooled by 2 fans that are inside of the enclosure. The main Pi 4 board is a plugged-in micro HDMI cable to the output, which is a monitor on top of the system. It's important to note that with this system, we can swap out any type of microphone as long as it's a 1/4-inch cable and doesn't require phantom power, which is an additional 48 volts to drive whatever microphone you're using. Taking a look at the actual video, we have the microphone here on the boom stand, the XLR plugged into the PiSound receiver. On top, we have the display, the keyboard, and the mouse, all plugged into the main Pi 4 board right here. On top, you can see the receiver with 2 potentiometers, one to adjust the volume and one to adjust the gain. In the back, we have the input where the microphone is plugged in, and right next to that, the output you saw was capable of plugging in headphones for the user to listen to. On the screen, we have data that's from a test. And right here on the bottom was the network port dock bay, and then in the side is the USB power supply. We have 2 fans surrounding the cluster. And then on the right side of the enclosure, we have enough room to tear down and store all of the exterior components inside of the enclosure for safekeeping.
Hi everyone, my name is Hussein Al-Darish. I'll be going over some of the requirements in the system requirements verification table. The first 2 requirements are for sound detection. We are able to detect sound in the desired frequency range and the desired sound level as shown in the slide. Next, we have the noise system requirements. We used a Pratt's specified filter, which is called pass-hand band filter with the mentioned specifications to eliminate noise in the recordings. For the calculation, we succeeded in calculating the high stress related acoustic features such as jitter, shimmer, zero crossing rate, and spectral flux using software Pratt and Pi audio analysis. We verified these calculations using MATLAB. The only system requirement that we failed to verify was requirement number 4.2.6.1, sound capture. We wanted the device to have a button that will allow the doctor to start and end the recording during the doctor-patient interaction session, but we failed in that. Another requirement that we passed was requirement number 4.2.6.2b. In this requirement, we have the system to automatically stop recording when the maximum time of 3600 seconds is reached. The last system requirement is the requirement number 4.2.8, which is the NLP. We have implemented a code that converts speech into text and create a file to contain the transcript of the audio.
Hi, my name is Jasper Jampalenka, and I'm here to do a quick demo of our system software integration. First thing I'm going to do is record an audio using our program for recording a session. I'm coughing. I'm coughing. We now have successfully saved our audio recording. The next step we're going to do is perform an audio segmentation using the Pratt software. We will load our newly recorded audio file into our Pratt software. And let's play it to make sure we have the correct file. I'm coughing. I'm coughing. The next thing we're gonna do is apply a filter in our audio using the reduce noise function. And let's play it. I'm coughing. As you notice, the background noise is now removed from the audio. The next thing we're gonna do is cut off any silence portion of the audio using the cut pauses function. And let's play it. I'm coughing. I'm coughing. As you have noticed, the audio is now truncated. The last thing we're gonna do is extract the voiced and unvoiced portion of the audio using the extract voiced and unvoiced function. As you have noticed, we have two new files, the unvoiced portion and the voiced portion. We are interested in unvoiced portion, and let's play it. And since we are interested on the unvoiced portion of the audio, we will save it as an audio or wave file, and let's name it as cuff.wave. The last step we're gonna do is perform an audio analysis. So we have wrote a program that calculates the audio feature of an audio, and I'm gonna be demoing one of the audio feature, which is the spectral roll-off. So let's check the spectral roll-off of our cuff audio. So as you can see, we have our unvoiced audio graphed using MATLAB, and the result for spectral roll-off feature of the audio.
Hi, my name is Dina, and I'm one of the biomedical engineers here in the team. Today, I'll be taking you through the tests that we conducted along with the future of the project. First of all, we did a settings test where we had the patient be between 1 to 3 feet away from the microphone, and we tested the pitch and the intensity, as you can see. Next, we measured the intensity over time for both male and female subjects, and we were able to come up with minimum and maximum values. We also did the same thing for frequency, which is pitch in hertz, for both male and female subjects. And then we also did a storage test just to determine how much the data would take, considering that a clinical interaction is usually around 17 minutes, and you can see the file size listed. I really wanted to go through the future of the project, and we really hope that the project is going to be utilized for diagnosing adventitious sounds, which are basically respiratory sounds that indicate pathology, such as asthma, COPD, or pneumonia. And this has been done in the past, actually not too long ago, back in 2018, where they were able to correlate the frequency of a wheeze, for instance, with asthma, COPD, or a foreign body. That's just as an example. And we really hope that the future teams would be able to pick this up and really help out physicians with diagnosis.